So in our previous analysis, we've had circular motion being generated by electromagnetic forces. So for example, you've got a positive charge, you've got a negative charge, just like atoms, right? Inside of our atoms, we've got protons and electrons, and they are spinning towards each other. We also have magnetic fields. So when we have some magnetic field and a charge with some particle with some charge going through that field, it will also feel some force, right? And now we could also have a circular motion because of gravity. That's actually the most obvious one. So we have Earth, for example, here, and the moon going around us. There will be some force trying to make the moon, between quotes, fall on us. We also feel a force pulling us up. For example, we can calculate the tides. We've got some phenomena in Earth that is caused because of the gravitational pull of the moon on the Earth. Well, anyway, if we make those equations the same, so let's say that we're making our centripetal force, which we know as mv squared over r, and our gravitational force now, which is capital G, capital M, lowercase m over r squared. Again, both forces, they're assuming point masses, so all masses concentrated at the center points. If you have two massive objects which size is not negligible, then you will have to take into account both radii. In this case, for instance, if this was distance d, I would have to take into account the radius of this and the radius of this large one as well. Alright? But if we assume that those are point masses going one towards each other, those will have to be the same. So if I make those equations the same, I'll have mv squared over r equal to capital G, capital M over m over r squared. And here I can straight away get rid of one of those things. So I get rid of one of the radii and the mass. So if I try, let's say that I want to know, okay, what's the minimum speed for that motion to be possible? If I want to put a satellite spinning around Earth, I could, just by using the mass of the Earth here. So how can I calculate that? Well, V, I already have my V here alone, so if I want to make it my subject, it's root of capital G, capital M over R. Alright? And that would be, for example, the speed of an object. If I want to throw something and this object to be able to leave the Earth, so this is the Earth, I'm going to put so much speed into something that it will be able to overcome the gravitational forces, the gravitational pull of our planet. So if we put the numbers in, we could just calculate any value for the velocity, escape velocity for any planet, any surface. Alright? Now, there's another interesting fact. We can get to Kepler's third law with this equation. If we notice, right, we may also use V equals omega r to get this in terms of omega. So if we square both sides, we can get V squared equal omega squared r squared. And now I can just rearrange this in terms of omega. So omega squared, right, would be, I'll put the r squared as well. Okay, so if I square both sides, I get rid of this root. So that would be capital G, capital M over r. Now, if I get this radius to the other side, I would have my omega squared, so my angular velocity or angular speed squared equals G mass over r to the power of 3. Now, if we remember that our angular speed is angular displacement over time, and that should be also, if I take a full turn, which is 2 pi radians, I would take my period in time to make that full turn. So if I take this relation here, I can get my period as my subject. So if I combine those two pieces of information, I would arrive at t squared is equal to 4 pi squared r to the power 3 over g capital M, where t is the orbital speed, or the orbital period, right? That's the time for one orbit of the satellite. And this is known as Kepler's third law, right? This proportionality between the square of the orbital period of a satellite and the cubed of the orbital radius. That's known as Kepler's third law. So now let's take a look at a few examples. So the first example here, calculate the gravitational field strength at the surface of the moon. And we're given the mass of the moon and radius of the moon. So this is quite simple. That's gravitational field strength is the force over mass. Alright? So in this case, it's capital G, uppercase M, lowercase m over r squared m. So the mass of our point object doesn't matter, and that's capital G, capital M over r squared. So you can use this straight away when, right, you're using a test object. You can go for this equation straight away, and if you put the numbers in, that would be 6.7. Again, since only up to two significant figures, I'll only put my constant up to two significant figures as well. So 6.7 times 10 to the negative 11 times the mass, which is 7.3 times 10 to the power of 22. Everything here is in SI units, so I'll not bother about drawing or writing the units, but we all know that it's this gravity here, or this acceleration, or gravitational field strength in the moon will be in the units that we expect, which will be meters per second squared or newtons per kilogram. So if we continue here, the radius 1.7 times 10 to the power of 6 squared. And if we work out those numbers, it would give us 1.7 newtons per kilogram, or meters per second squared. So another example, calculate the gravitational field strength of the Sun at the position of the Earth. So mass of the Sun is given, and the distance between the Earth and the Sun is also given. So again, G equals capital G capital M divided by R squared. So constant 6.7 times 10 to the negative 11 times mass 2.0 times 10 to the power 30 kilograms. Everything is in SI units. All of this divided by r squared, which is 1.5 times 10 to the power of 11 squared meters squared. Now, we notice that we're only taking into account the distance between the Earth and the Sun. We're not really using the radii. It's because if you compare to the distance between them, the radii is negligible. It's very, very small compared to this distance between them. If we work out those numbers, then we would get 6.0 millinewton, so 10 to the power of negative 3 Newton per kilogram. Okay, so calculate the orbital period of Jupiter about the Sun. So we're given the mass of the Sun and the radius of Jupiter's orbit. So here in this case, we'll have to apply the equation that we have just found, right? That proves Kepler's third law. So it's the period squared. If you ever forget, you can get to the equation, because you should have all the tools which are necessary for you to get back to that equation. However, I'll just put it back here. So 4 pi squared r to the power 3 over g m. So we're given the mass, we are given the radius, and this is a constant. So it's just putting numbers in. So that would be 4 pi, then radius, so 7.8 times 10 to the power of 11 to the power 3 over, pi squared, over 6.7, again, two significant figures, times 10 to the negative 11 times the mass, 2.0 times 10 to the power of 30. So this would be 3. Oh, no. If we worked the root here and get just the period, then you can check your values. The period should be 3.7 times 10 to the power of 8. And since we've used all SI units, that would be seconds, which would be roughly 12 years. Okay, so the last example, we've got the orbital time period of the Earth about the Sun is 3.2 times 10 to the power 7 seconds. Calculate the orbital period of Mars. So we're given the radius of Earth's orbit, and we're given the radius of Mars' orbit. So again, it's a similar relation, isn't it? There are some things in this equation which are constant. So if you look at it, t squared is equal to 4 pi squared r to the power 3 over g capital M. Right? Now, since we're looking at two planets which are orbiting the Sun, this is the mass of the Sun for both of them. Right? So this capital M is the mass of the Sun. So if we observe this first portion of our equation, all of those values, they should be constant. 4 is a number that's constant, pi is constant, capital G, that's our universal constant, right? Gravitational constant. Capital M is the mass of the Sun, which will not change on those two analyses. So I could basically say that t squared over r to the power 3 should be constant for all planets which are going through around the Sun. So we can compare those two. Since I know the radius of Earth, I would know the radius of one of them. So let's say if I put it down, that would be t squared of Earth over the radius of Earth to the power 3. That should be equal to the period of Mars squared over the radius of Mars to the power 3. And now, if we're looking for the period of Mars in terms of everything else, I can take period of Mars as my subject. So it would be the period of Earth and square root of radius of Mars to the power 3 over radius of Earth to the power 3. And if you just put those numbers in, you should find this to be approximately 6.1 times 10 to the power 7 seconds, which would be approximately 1.9 years. Now, it's actually funny to observe that this Kepler's third law was thought of only by using empirical data, only by using analysis, just by using verification. So people would observe, they would get their telescopes, they would look at the objects that we had, or the planets, how long did they take to make a full turn around the Sun, and just by using that empirical data, Kepler was able to design this equation. And then only later on, but decades later, then Newton actually got to it, and using theory, he got to basically the same proportionality that was observed before by Kepler in an empirical way, so from experimental data.